Testing. 1, 2, 3. Should hopefully pop up on Max's screen.
Wait, do you want to log on to your?
Oh wait, that's wrong.
I hope you do have the what's it called, slides.
No, I can like. I'll find a way to get the slides. It's fine. I'll like go into Overleaf and then maybe download it. All right.
Wait, so Max, can you see like the image on my screen or the?
Have you started?
Yes. Like if you click into it.
Oh yeah.
Oh, okay. Cool.
Yeah, the audio is good.
Okay. Wait, can I see the? Right. Cool.
Yeah.
It looks fine.
That's good. What software are you using to connect your tablet?
I was using like an AirPlay stream mirroring.
Oh, okay.
Yeah.
I was just I'll do it next week.
Yeah, which we should found online.
Okay, what's it called?
It's just called AirPlay screen mirroring.
Screen mirroring.
Yeah.
Oh, okay. All right.
Yeah, just like just in case when I'm writing an expression, you have to do this.
That's fine. I left plenty of space.
So is this count just when the two rows part you can just upload pictures? And then that is if the two rows are different for different ones. So he's an all different part of the whole. I've only ever talked about it and doesn't matter what it is. I mean, unless it's like almost like oh yeah. So it's just transfer is this how it's kind of how you draw? It should be able to draw it without make that. If you can have yeah. I mean, the other parts of the thing for furniture. I mean, as long as like you know, as long as
Of course. Oh, Preston.
just no branching, just 2 inches.
Do you even do 1 for 1? Do you even do 1 for 1?
Does it matter?
No. Yeah, who cares? He doesn't bet, right?
Oh, really?
Yeah.
I respect it. this week too, actually. Did you do 1131?
No,
4-1. Okay. Yes, you know, get like 100% on the exam bank like 5 times in a row. That's when you know you're ready, right?
I think you should be fine now.
Okay.
Okay. Hopefully.
Alright, cool. So let's go on to this question here. I have a parallelogram with side lengths 1 and 3 units. So if we take the length of both of the diagonals of the parallelogram and square each length, the difference between the squares is 6. Find the acute angle between two non-parallel sides. Now, the tricky thing with like math, as far as I see it, right, is you learn all these concepts and formulas in class, right, in like the lectures, and even back in like high school in class and whatnot, right? Teacher just tells you, okay, learn these formulas, and then just, you know, figure out how to use them, right? But when it comes to the actual exam, right, and you have to, you know, interpret questions and the words in the questions well, that's when the challenge starts to pop up, right? And so let me just give you like an insight into how I view these exam questions, right? Okay, so let's read the final line, because usually that's the most important one, right? It's asking you, literally asking you what to find. It says, find the acute angle between two non-parallel sides. Well, if we want to find the acute angle, right, usually we want to use the dot product. So that already gives us a clue, right? So we want to use the formula, right, where cos theta equals A dot B over the magnitude of A times the magnitude of B. So that already gives us an insight into what we want to do, ready? And that's probably like one of our final steps, right? But what do we not know yet, right? Well, if I just let vector A and vector B just be the sides of the parallelogram, right? It's pretty easy for me to find what the magnitude A and the magnitude B is. It's literally in the first line of the question. You have side length 1 and side length 3. So that's done, right? And just by interpreting the question. So what do we not know yet? We do not know what A dot B is. And so if you want to find out what A dot B is, clearly the clue lies in the second line of the question. Taking the lengths of both of the diagonals of the parallelogram, squaring them, and then taking the difference is 6. Okay, so I'm just going to let arbitrarily let this be like vector A, let this be vector B. And I'm just going to also arbitrarily let the angle between them be acute as well, because it's convenient for me. It does not matter. And so I'm going to take these to be vector A and vector B. So I'm going to take, okay, the diagram's not to scale, but let's let mag A equal 1 and mag B equal 3. And so what do I get here, right? And from the second line, if we interpret that mathematically, what we get is the diagonals of a parallelogram can be expressed in 2 ways. So we take the sum of vectors A and B to get the first diagonal. So this is A plus B. The second diagonal, I will just take arbitrarily A minus B. So we just go from B to A. And so I get, since the A plus B diagonal is longer, because the angle between A and B is acute, so I'll have the magnitude of A plus B squared minus the magnitude of A minus B squared. And that will equal 6. So that is just interpreting the second line. Now, what important factor to tell you about the dot product earlier? There was a really nice result where if we had a vector and we dotted it with itself, we would get its magnitude squared. And so we can apply that exact property here, because A plus B and A minus B themselves are their own separate vectors. Like you can consider them as one whole vector, right? And so what we can get is that A plus B dot A plus B minus A minus B dot A minus B. Now will equal 6. Oh, that is... And so, the next important property of dot products comes into mind here. We want to distribute it. And so, if we distribute the dot product across, and I'm just going to like skip a few like steps you would probably formally write in like high school or something, right? But in uni, we're doing most of our exams like Maple and MATLAB. Doesn't really matter, right? And so, I'll get the magnitude of A squared, because that's from A dot A, plus 2 times the dot product of A and B, and then plus the magnitude of b squared minus the magnitude of a squared minus 2a dot b plus the magnitude of b squared, and that will all equal 6. And so, there's a couple of terms I can already eliminate. The magnitude of a squared and the magnitude of b squared get eliminated because you just have their negatives in the second expression. And then the only expression you have left is a dot b. So you get 4 times a dot b equaling 6. And so what you find is that a dot b will equal 3 on 2. And so we found our final unknown required to compute the dot product angle formula, being cos theta equals a dot b over magnitude of a, magnitude of b. And so we know those results to be 1 and 3 respectively, because it's given in the first line of the question. You have a parallelogram length 1 and length 3. And so what I get is 3 on 2 over 1 times 3. So 3 on 2 over 3 is just half. And using our exact angles of cos, which we all, memorized back in the day, hopefully, we get theta equals to pi on 3, or like 60 degrees. And that is the acute angle between the two sides of the parallelogram. We essentially interpreted, right? We took like a kind of difficult looking question, carefully broke down and interpreted each line, right, and what it required from you, mathematical skills wise, right? Last line, we want to use a dot product for the acute angle. First line, it gives you within that formula the magnitude of A and the magnitude of B. And then second line, you can derive A dot B. See how it all comes full circle? And so that's how we essentially approach this question, even if you're a bit confused by the wording. Just stay calm and break things down, yes? Any questions about that? Alright, I'll move on. So we find the angle to be 60 degrees. It's seen there. Let's move on to another key result where we find relationship between two vectors. And this is the cross product. So the cross product between two vectors A and B is defined as that, algebraically. The significance of the cross product is that it gives you it outputs a vector which is perpendicular to both the vectors you input. So essentially, right, if we have A cross B, then we'll get a vector, A cross B is perpendicular to both vector A and vector B. So that is the significance of the cross product. Now, you need to be careful with the cross product as well. There's like the results that apply in dot product, such as commutativity, doesn't exactly apply in cross products. And so you need to be careful about potentially using those laws. And so, but the most important thing to memorize is that A cross B gives you a perpendicular vector to A and B itself. And so in terms of actually applying that, let's go read a question. Oh yeah, also just one more thing actually. An easy way I always found to compute the cross product is this way, right? So we have A cross B, right? A1, A2, A3 times B1, B2, B3. In my head, right, I would essentially like draw, right, A1, A2 again, right, and then B1, B2. And essentially what I did was I did a bunch of crisscrosses here. So 1, that's the first crisscross, right? So it's A2 times B3 minus A3 times B2. Take the second crisscross here. And so A3 times B1 minus A1 times B3. And then take the last crisscross here, which is A1 times B2 minus A2 times B1. So that was always my trick for using cross product, even when I used it like back in high school as well. And so that reflects this result here. Just quickly, does anyone have any questions about like this like little trick I'm showing here? Because this was not technically in the seminar, it's just something
I'm showing you. Any questions about that? So you can put the first and second components of each vector just below, right? And then you can, I visualize it mentally, but you can also just write it down and then do the crisscrosses. Is that all good? All right. So let's move on to a question applying the cross product, right? Well, that first one is a dead giveaway. So find the magnitude of this vector CB. So the vector CB is just the vector OC minus OB. And yeah, a bit counterintuitively, we take the first one and minus the second one, but sorry, it's vector OB minus OC, right? So like it's a bit counterintuitive, but we take like the second part of it and then put that first, right? So if we have CB equaling OB minus OC, what we essentially get is 0 minus 4, 4, minus 2 minus 2, 3. So we get minus 2, and 1. And so what we essentially get as our magnitude of CB, we just compute the magnitude, we will get just 3. Because this is 4 plus 4 plus 1, that's 9, the square root of 9 is just 3. Also, just in case you like fumble a little bit, like I did just then, in terms of like OB minus OC, that's actually perfectly fine. Because the magnitude, in this case, right, the magnitude of vector BC is actually equivalent to the magnitude of CB anyways. So even if you like trip up and fumble on that, doesn't matter in the end. You'll still get the correct magnitude. Yeah. Sorry? Oh, wait. Yeah, I seem to have chosen the wrong vectors. My bad. Good catch. So I will get minus 3, minus 9, 4, 9. That's root 106 as our magnitude. Apologies for the error. Alright, now to approach the second part, which is a little bit more difficult than the first one, right? We're going to find area of the triangle with vertices A, B, and C. Now, how do we actually approach this? I probably didn't teach you guys the cross product for no good reason, right? So for me, you right? Yeah. We want to use it. And so how do we actually use the cross product in this case? Well, let's just visualize the triangle ABC first, right? So let this be A, B, and C. So we can already construct, right, like the vectors AB and AC themselves. And there's a couple of ways we can do this question, actually. Not just with cross product. But for simplicity's sake, I will do the cross product method. And then maybe I will go into some other methods as well, just in case you guys forget the cross product. And so the area of this triangle, right, you'll find is if you take the cross product and its magnitude, you'll find that you actually get the area of this parallelogram. The magnitude of the cross product essentially gives you the area of a parallelogram of the two vectors, formed by two vectors. And so, if you want to take the area of the triangle in this case, which is half the area of the parallelogram, we just get our formula to be half of the magnitude of the cross product between AB and AC. And so that's the step we want to take in terms of finding the area of this triangle. And so as area equals half AB times AC, what we essentially get is half of, so first compute AB, which will be minus 2, 1. I'm certain of that this time. And then AC being 5, 7, and negative 3. Wait. No, that's 1. 1, 7, negative 3. And so we compute this cross product below, right? And I'm just going to use like my crisscross trick to quickly find the values. So that should be half of the magnitude of this vector, minus 1, minus 5 minus 12. If anyone wants to verify that result for me, that would be cool. And so, if I compute this magnitude, what I will get is root 170 on 2. And so that becomes the area of our triangle. Any questions about that?
It should be a plus 5.
Plus 5?
Yeah, minus 5 plus 5.
You sure about that? No, wait. No, that one is 1 times 1 minus 2 times minus 3. That should be minus 5.
Which one? The middle.
Yeah, the middle term should be minus 5.
Oh, I think that's fine.
It's all good. It's all good. That's all right. It's all right. It's all right. All right. Here's some alternate methods of approaching this question, just in case, you forget your cross product in the day. Pressure is high, right? Your backs are against the wall. Last question, make the difference between pass and fail, right? What do you do? Well, here's some other methods. Well, first method you can take is you can take a projection, right? Because what's another way we can find the area of a triangle, right? We just get its perpendicular height and multiply by the base. If you consider that in a vector context, right? If you have this vector A, B, and C, right? The base itself is just the magnitude of vector AC, right? And so if we project AB onto AC, right? We get this projection here. Oh, that is too much. We get this projection here. And then we can take the subtraction between the vectors AB and this projection, and then take the magnitude of that to get the perpendicular height. And so that is another way you can potentially approach this question, and then multiply that by the magnitude of AC for the base. So that's half times base times height. So it's exploiting that formula. And so what does that look like in this case? Well, we get the area to be half times the base, which is the magnitude of AC, times the height itself, which is AB minus the projection of AB onto AC, which will be this, this minus this, which gives you like this. And so we take the magnitude of those subtraction of vectors, and so what we get here is half times, what's the AC? That would be 17 minus 3, magnitude of that being root 59. And then AB minus the projection of AB onto AC. So AB being minus 2 minus 2, 1. And then we minus that by the projection, so minus 2 minus 2, 1, dot my 17 minus 3 over 17 minus 3 dot 17 minus 3 using the projection formula. And so if we compute all of this, we get half root 59 times this vector minus, let's see, quick math, plus minus 2, 19 on 59, 17 minus 3. Okay, this is a bit cumbersome at this point, and I do not want to progress with this. I want to move on to my next question. But if you verify this result, you will actually eventually get root 170 over 2. And so that is another method you could approach this area of a triangle question without even needing to use cross product, just in case you forgot how to compute it or something, or forgot its significance, geometrically as the area of a parallelogram. And then you multiply that formula by half to get the area of the triangle. Are there any questions about this one? Alright, then I'll move on. So the last part, hence or otherwise find the shortest distance from the point A to the line passing through B and C. So if I have this being point A, right, and then this is B and C, if we look at this case, we can find that the shortest distance is found when A is perpendicular to BC. And how do I know this to be the case? Well, it's by simple Pythagoras theorem, right? AB as hypotenuse of that right angle triangle must be larger than this distance here, right? And likewise, if you take any vector from A to any other point on BC, you'll find that is another hypotenuse, which is always going to be larger than this line here. So I know that the perpendicular distance is always going to be the smallest. I know that by fact. And so what I essentially get here is we want to find the perpendicular height essentially of this triangle, right? But let's think about it. In the previous parts, we have the magnitude of CB. Notice that this magnitude CB is kind of like the base of this triangle, right? And then in the second part, we have the area of the triangle. And so we can reverse engineer essentially, right? The area formula being A times half BH, and essentially get H equals 2A on B. Now, what is A? Well, we know that to be root 170 on 2. And what is B? Well, we know that to be the magnitude CB. And so, what I essentially get is, right, H equals root 170 over root, what was CB? That was root 106. So, if we simplify that, we get root 85 on 53. And then that becomes our height, just by simply reverse engineering the area equals half times base times height formula. It's easiest and it's the quickest method to approach this question based upon the previous parts. But if a question says like hence or otherwise, like in more than like 70% of cases, it's most likely that you're gonna use the hence. Do you guys understand? Alright, any questions about that? Alright, and so we verify our answers here. Lovely. Alright. Actually, I apologize for introducing like the projections without first talking about it. But I thought that was necessary to introduce another method for you guys. And so last little thing here, so the projection of the vector A onto the other vector B is defined as such. Proj of A onto B equals A dot B on B dot B. And that as a scalar multiple of B. And so if we take the magnitude of these two, of both sides, we get the scalar projection, which is the length. And what does it actually look like in an actual sense? So if we have this vector A, and then this vector B here, the projection of A onto B will look like this. That's just what the projection formula essentially computes, is the orthogonal component of A, which is in the direction of B itself. And what do I mean by orthogonal components? Well, just look at this, right? Here we have 90 degrees. And that looks very similar to like the linear combination we have between like I and J, for example, right? Because we can express every vector in terms of I and J, right? Where these are perpendicular orthogonal components. And projections exploits the exact same fact. You have the orthogonal components in this case, but the caveat being is that it's in the direction of B itself. And so that gives you this kind of line here. And so we go into our last question, the distance between the two skewed lines. So if you want to find the shortest distance between these two lines, well, let's think about it, right? We had our kind of fact before, right? Where the perpendicular distance between, like, let's say a line and a point, right, was the perpendicular one, right? And I also stated how that is an absolute fact, because you can, by Pythagoras theorem, you can draw like a line from a point not on the line to another point on the line, and then also the perpendicular. That forms a right angle triangle, and that hypotenuse is always longer. So the shortest distance is the perpendicular distance. And so we want to exploit that fact in terms of approaching this question, right? Skew, by the way, skew lines satisfy two conditions. So skew means that they are not parallel and they are also not intersecting. Okay, so not parallel, not intersecting. So essentially, it's this kind of scenario, right? Where I have like a line here, and then imagine this is underneath the line, right? And then like this passes over, and then they do not intersect, and they're not parallel. So it's this kind of scenario. But that's not an intersection, by the way. Please don't take it as such. Imagine that it's a bar, right? And so to find the shortest distance between the two skew lines, you must find a vector between them that is perpendicular to both lines. Because the shortest distance is going to be perpendicular to both lines. And so, how do we actually approach doing that? Well, first, we want to find a vector that is perpendicular to both lines. And so, we take the direction vector of both lines, 4, minus 7, minus 6, and minus 1, 1, 3. And so, what we get is their cross product. We compute their cross product to find a vector perpendicular to both direction vectors. And so, what we get is 4, minus 7, minus 6 times minus 1, 1, 3. That will give you minus 15, minus 6, and minus 3. So I know minus 15, minus 6, minus 3 is our cross product between the two direction vectors, and that this is perpendicular to both lines. And, if you want to be pedantic, I can verify that by taking the dot product between that cross product and then each individual direction vector. And so what we do after this, right, is we apply our projections formula. I'm going to first, right, take some arbitrary vector between the two lines. And we have to take that between 2 points on the line, right? And then the easiest example there is just their position vectors, right? So a vector between the two lines, so I'll just let this be n, and then a vector between the two lines is minus 5, 8, 7, minus 9, minus 7, 2. That will equal 4, 15, 5. And so, with this vector between the two lines, right, that is obviously not our shortest distance. We know that to not be the case because it's not exactly perpendicular to both lines. And so, in terms of showing it diagrammatically, right, I have this vector between the two lines, right? And then I also have the vector which is perpendicular, right, to both. So, what can we do? Well, in this case, we want to project this vector here. We want to project this vector between the two lines, but you want to project it onto a vector that is perpendicular to both direction vectors. Now this might seem a bit strange, but let me explain it, right? I said earlier that a projection as a formula means finding orthogonal components in the direction of another vector. And so, if I want to find the shortest distance, I said earlier that it needs to be perpendicular to both lines. So essentially what we are doing is we're finding a vector by computing the projection between these two things. We are finding the vector between two lines, but is also in the direction of this cross product here, in the direction of this cross product, because we want it to be perpendicular to both lines. And so that will give us the vector between the two lines, which also has the smallest magnitude. Does anyone have any questions about that? That was like a lot to consume. Like, please be brave. It's fine. Yeah, of course. That's fine. I said earlier that a projection, right, was finding an orthogonal component in the direction of another. So if I take, right, the projection V onto N, then I'm essentially finding the orthogonal component of V in the direction N. And why do we want this to be in the direction N? Well, for the shortest distance, we need a vector that is perpendicular to both lines. And we verified via the cross product that N is perpendicular to both lines, because it's perpendicular to both direction vectors of the line. And so, if we find a projection V, which is the vector between, like, just the two lines, any arbitrary vector between the two lines, right? And then we project that onto the vector N, it's essentially taking a vector between the two lines and then minimizing it, in a sense, to the perpendicular distance. Was that all good? Any other questions, guys? This is like pretty difficult. Okay, I'll move on then. And so, since we're just finding the shortest distance, there's no need to actually compute the vector itself. Just take the scalar projection, right? And so that will equal the magnitude of v dot n over the magnitude of n. So what does that equal? Well, v dot n itself will equal to minus 60 minus 90 minus 150 minus 165 over the magnitude of the vector n. And so that will be over root 270. And so if we take that value, then that will be 165 over 3 root 30. And so we essentially get our final answer, 55 on root 30. And that will be our shortest distance between the two lines. So just to recap quickly on this question, right? If you want to find the shortest distance, we first establish, right, that we have to find a vector obviously between two lines. But that vector also has to be perpendicular to both the lines. And so if you want to find that vector, we first find the vector which is perpendicular to both lines, which is through the cross product. Then we take an arbitrary vector between the two lines, right? So which is just n between any 2 points. We just chose the position vectors for simplicity. And then we project that position vector onto the cross product, because we want to find a vector between two lines, but that is also parallel to this cross product, because we want to find a vector between the two lines, but also perpendicular to the two lines. Do we understand the purpose of using this projection formula? Yes? Okay. And then so we compute the magnitude of that projection formula, and we get our final answer, 55 on root 30 units. And that should be right. So that concludes my section on introduction to vectors and vector geometry. Hope you found that to be informative. And so I'll pass on to Jenny now for matrices and complex numbers. Thank you, guys.
Just quickly, everyone, feel free to grab these as well.
Yes, good luck.
Provided, so,
Good luck there.
Oh, yeah, thanks.
and these you like.
Okay guys, that concludes the first section, which is on mainly vectors and vector geometry. I'm going to take you guys through the second, or a really important chapter in 1131, 1131, and 1151, which is matrices and matrix operation. So essentially what matrices are, even though we don't really have that slide, is they're really just blocks of numbers that represents the coefficients of linear systems. So for example, a matrix like if we have a linear equation like, let's say, x plus y equals 1 and 3x plus 2y equals 5, how can we represent that using a matrix? Is basically we're just taking the coefficients of those variables. So we have 1, 1, 3, and 2. And then using an augmented matrix form, we're essentially writing a line in the middle to kind of notate the separation or equal sign. And on the right-hand side, we just take the 1 and 5, which are the constants in our original linear equation. So this is how we can use an augmented matrix form to notate a system of linear equations. Okay, so this is kind of like sort of the basics of matrices. I trust you guys should be familiar with that from the lectures. So we'll actually just move on to a question that involves some different operations on matrices. So here we have two different matrices, P and Q, where P is a 2 by 3 matrix because we count the number of rows first, and that is a 2, and we have 3 columns, whereas Q is also a 2 by 3 matrix. So first of all, we want to evaluate the products of P times the transpose of Q. So just a quick revision for you guys. Essentially what a transpose is essentially we're taking, so QT is we're taking the rows and making them the columns in our new matrix. So how do we kind of like see that, visualize it as we write it down? Essentially, we're taking we're taking the columns and then making them the rows. Oops. Right. Okay, there's a drastic color change. But anyways, we're taking the columns and then making them the rows in the new matrix. So first of all, we're taking this 1, 2. That means our new first row in the transpose of Q will be 1, 2. And then we're taking this column, which is negative 1, 5. So we have negative 1, 5. And then finally 1, 0. So this will be our new transpose of Q. And then essentially for part 1, we want to compute what P multiplied by the transpose of Q is. So then we just write P and Q again. That is 1, 3, 2, negative 1, 1, 4, multiplied by 1, 2, negative 1, 5, and 1, 0. So essentially what matrix multiplication is we're taking the individual rows in our first matrix, and then we're multiplying that. We're essentially finding the dot product of those with the second individual columns of our second matrix. So this is why when we have a matrix of, let's say, m multiplied by n, where m represents the rows and n represents the columns, if we want to multiply that to a new matrix, our new matrix must start with n number of rows because they must match for us to be able to perform that calculation, right? And then it could be any number of columns. Okay, so just quickly computing that, then we will have 1 multiplied by 1 plus 2 times negative 1 plus 1 times 1 in our first column, and then we'll have 1 times 2 plus 2 times 5 plus 1 times 0 in the second, and then 3 times 1 minus 1 plus 1, plus 1 plus 4, and 6 minus 5 plus 0. So that would be our new matrix, which if you simplify the numbers a little bit, you'd be able to get, that's 1 plus 1, that's 0, 2 plus 7, which is 9. Yeah, I'm very bound to make silly mistakes here because it's a bit hard to read right now. Oh, that's actually 12. And then 3 plus 4, that's 8, and that should be 1. So that would be our new matrix product of P multiplied by the transpose of Q. So essentially, this operation is pretty simple. You're really just taking each row in your original matrix and then multiplying that by each column in your new matrix to get to your final product. And then our part 2 of the question is asking for us the size of the transpose of P multiplied by Q. So because that, first of all, we have a transpose on the P here. So this is actually not identical to the first question. And also if we swap, by the way, if we swap the positions of P and Q, you're actually going to get a different product. So just be aware of that in matrix calculations. But we want to find the size of transpose of P multiplied by Q. So let's actually notate transpose of P first. So we have transpose of P should be equal to 1, 3, 2, negative 1, 1, 4. So this is a 3 by 2 matrix, right? And then we want to multiply that by a Q, which is a 2 by 3 matrix. So recall that when we're multiplying an m by n matrix with an n by p matrix, then our final matrix would be n m by p matrix. So essentially the n is kind of like the connecting thing here. So as we can see, the middle numbers match. So in this case, we're just going to get a 3 by 3 matrix for our final transpose of P times Q. So we really don't have to find what transpose of P times Q actually is. You can just kind of figure that out by looking at how many rows and columns each matrix has. Any questions here? No? Great. Okay. And then finally, we have a question asking whether the matrix product of P times Q exists. So to determine if the matrix product exists, we really just have to find if like this middle number n matches up for both of them, right? So if we look at just P and Q, remember we said they are both 2 by 3 matrices. So if we multiply a 2 by 3 matrix by a 2 by 3 matrix, that wouldn't really make sense, right? Because here you have 2 rows, which you need to be multiplying to each column, but then here you have 3 columns. So there's going to be an additional column in the second matrix. That's going to go nowhere. So essentially, then we cannot multiply the matrices P and Q, and therefore their products would not exist. So it does not exist. And that really concludes our first example, which is mainly kind of a recap of what matrix transposes are. Here is the formal written solutions. Yep. Wow. Okay. And then moving on, we'll be looking at a very important part of matrix, which is row echelon form. So essentially, this is kind of like a simplified matrix form. As you can see, let's say we have a matrix of 1, 1, 0, 0, 1, 1, 0, 0, 1. Right, this is just a very simple matrix, right? But if we look at this matrix, it is actually in row echelon form because as you can see, in every column, if you look, below the leading entry, which is the non-zero number, you have always zeros. If you look at the second row, below the leading entry, which is this one, you always have a zero below it, and then so on. So essentially what row echelon form is, you've reduced a matrix by performing some sort of like linear calculations such that you can get there's a leading entry and leading rows and leading leading columns. So these are just kind of special terminologies. It basically just means all the non-zero entries in the matrix. So it might be easier for you guys to look at this with an example. Just a bit of theory before we go on to the example is that once you reduce something to its row echelon form, which is generally in the form of quick example being, let's say, 1, 2, 3, 0, 4, 5, and then 0, 0, 1. Let's say we have a matrix like that, right? And then we have a line here, and that's equal to 1, 2, 3. So that's completely random numbers. But pretty much once you reduce it to this form, you can kind of look at this form and determine how many solutions are we going to have to this linear system. So how do we look at that? Essentially, if you look at the right-hand column, which is basically this column, if the right-hand column is a leading column, which actually means you have a matrix something like this. Let's say you have a matrix like this, right? So in this case, where would the leading column for row 2 be? That would be the right-hand side column because every other entry to the left of it is all 0. So in those cases, when you have the right-hand column being a leading column, we'll always have no solution because if you visualize what this means, this essentially means some variable x, 0 of that plus 0 of some variable y equals 2, which is impossible, right? Because we can't have 0 plus 0 equals 2. So this is why you're always going to get no solution if the right-hand column becomes a leading column. That's the first scenario. Secondly, we can also have unique solutions for matrices. So this is when every column on the left is a leading column. So essentially you're looking at every column and then you're determining if they are leading columns, which how do you look at that is basically that below every number, which let's say below every this number and then this number, you should always get 0. In which case, in this matrix, we do have that satisfied. So we're really just looking at the first like non-zero number across every row. So you would get a unique solution if every column on the left is a leading column. And finally, you would get infinite solutions in any other cases. So essentially, you just have to determine whether it has no solution or a unique solution, because otherwise it's going to have infinite solutions. Right, so that's a quick recap. And then let's take a look at one question. So we have 4 real parameters, a, b, c, d, which represents the coefficients of x, y in a curve. So they pass through this curve. You're told that it passes through 3 points, which is a, b, and c. And first of all, we want to explain why the following equations can be used to determine the values of a, b, c, and d for which the curve passes through. So essentially, for matrices, we're using matrices to solve geometric and vector problems most of the time. Right. So first of all, if we know, we want to start from the given, right? We know that this curve passes through the points A, B, and C, which means if you substitute the coefficients of, if you substitute the values of x, y coordinate in A, B, C, that should satisfy our original equation. Right, which means if we substitute 1, 1 into ax squared plus by squared plus cx plus dy equals 1, that should satisfy the original equality, which means it should be true. So this is what gets us our first line, which is when you solve in x equals 1 and y equals 1, and you'll be able to get that equation. And then essentially you're also subbing in x equals 2, y equals 3, and x equals 0, y equals 1 to the remaining, to get to the remaining linear equations. So then we have this sort of system of linear equations where we have 4 variables, or really only 3 equations. So that's important to note. Okay. And then in part 2, we want to use Gaussian elimination to solve the system of linear equations in part 1. So what Gaussian elimination is essentially you're just reducing it to row echelon form such that you can get all of your variables by back substitution. So how do we do that? First of all, we want to write that as a matrix. Let me just quickly remember the numbers. 1, 1, 1, 1, 9, 2, 3. Okay. Oh, oops. Okay. So let's say we want to first convert that into a matrix, which is 1, 1, 1, 1, 4, 9, 2, 3, and 0, 1, 0, 1. And on the right-hand side, we have 1, 1, and 1. So now we want to start reducing this matrix to its row echelon form, such that we can determine at least one of our variables, which in most of the cases will be D. So what we can do first is actually, we have this matrix in a very favorable form because, as you can see, the first entry on the top left is 1, right? We always want to have 1 or -1 on this position. So then what we can do essentially is we can do row 2 minus for row 1 to get rid of this 4 below the 1, which is when we start reducing it to its row echelon form. So then we would get 0, 9 minus 4, which is 5, 2 minus 4, which is -2, and 3 minus 4, which is -1. The top row stays the same. On the right, we have 1 minus 4, which is -3, but everything else stays the same. So I find it easier to do it in steps instead of combining everything in one step because then it's really easy to make some sort of algebraic mistake. But then we have our new matrix in which we have a leading column here already. So now, once we have this leading column, we want to start looking at the column right next to it and then start reducing all the entries below the top row, right, and the second row. So in this case, what can we do to that? We have 5 here, but 1 here. And remember, this is actually our second pivot point. So we always really want to have a 1 or -1 on our pivot points. So in this case, what is actually favorable to do is we want to swap rows 2 and 3 such that we can get the pivot point. So that's 0, 1, 0, 1, 1. Oh, oops. Yeah, 1, and then we have -3 is 1. So essentially all I've done is we're swapping the second row with the third row to get the 1 there. And then what we can do is we can do the third row minus 5 of the second row to get to our new matrix, which is going to be 1, 1, 1, 1, 0, 1, 0, 1, and then 0, 0, -2, -1 minus 5, which is -6, and then we have 1, 1, -8. And then that will be our new matrix, right? In which case, we pretty much can't really reduce it anymore because notice how we have a 0 here and we can't really cancel out like those two in any possible way, right? So this is pretty much all we can get. And that will be our sort of final form in row echelon form. Okay, so just by looking at this, we want to determine if there's 0, 1, or infinitely many curves that kind of satisfy this form that passes through ABC. So essentially, you just want to find, do we have a unique solution or 0 solutions or infinitely many solutions to this matrix that we have here? So we look at this matrix. First of all, you see that if you look at every column, it's actually not every column is a leading column because you have a -2 below 0 there, which creates a problem, right? So essentially, because not every column is a leading column, and also because on the right-hand side, you don't really have like the right-hand side as a leading column either. So then, in this case, looking at our theory, we'll be able to get infinite solutions for this matrix. This is also pretty intuitive if you just think about it. So we have 4 variables, but then we gave you 3 equations. So we know to solve 4 variables to get a unique solution, you at least need 4 equations, right? If you have any less, you're going to get infinite solutions. So this is why we'll be able to get infinite many curves of this form. And then finally, we want to use our answer from part 2 to find a parabola of the form y is equal to alpha x squared plus beta x plus gamma, So essentially, we're just like using this matrix that we just determined to find the values of A, B, C, D in that curve that we had. So what we can do is, actually we can simplify this further, but what we can do is, then we would really have A plus B plus C plus D is equal to 1, B plus D is equal to 1, and negative 2C minus 6D is equal to negative 8. So since we know there's infinitely many curves, we can actually like just find any random curve. So one such curve that we can find is if we let D be equal to 1, and then we want to find the corresponding C. So then negative 2C would be equal to negative 8 plus 6, which is negative 2, and C would be equal to 1. And then we can find B as such. So B should be equal to 1 minus 1, which is 0. And finally, A should be 1 minus 0 minus 1 minus 1, which is negative 1. So one such curve that we could get, I'll just show you guys, in the solution is when we sub in the value of D equals 1 and then get the corresponding values of A, B, and C. And then finally, you want to put it into the form of whatever they asked us in the beginning, right? So essentially subjecting Y, so we just move everything to the right-hand side. So what's important to note here is that this is obviously not the only unique solution. You can get any other solution that you would like, and that would be correct as long as you did the algebra right. So that's this question. Do we have any questions? No? Great. Okay. Now we're moving on to some more complicated operations on matrices, or I guess concepts, which is the determinant of a matrix. So just a quick recap. Essentially, when we have a 2x2 matrix, because that's just easiest for us to write the determinant, if we have a higher row and column, it would be harder to write it out. So the determinant of this would essentially be AD minus BC. So you kind of do the cross multiplication of the diagonals to get the determinant. So for AB, which are two n by n matrices, recall that why do they have to be two n by n matrices? Because to do their matrix products, we really have to match like the inside, the rows with the columns, which is why they have to be defined as such. Then the determinant of AB is equal to the determinant of A multiplied by the determinant of B. So there's some complex algebra in this, but essentially you can prove it by, let's just like say, let matrix A be like A, B, C, D, and then B be like E, F, G, H. And then you can do the algebra yourself, so I'm not going to go through that because that's going to take quite a while. But you'll be able to prove that this identity. What's another interesting identity is, so basically the determinant of a transpose of a matrix is just equal to the determinant of that matrix. So this is pretty much because if you have, let's say, A is equal to A, B, C, D, then the transpose of A would be equal to A, C, B, D, in which case, because multiplication is commutative, if you calculate the new determinant of this matrix, you're still going to get AD minus BC, which is the exact same determinant as our original one. So this is why this property holds for matrices as well. What's also important to note is that if a matrix is invertible, that only happens when its determinant is not equal to 0. So what invertible means is when you have a matrix A, you'll always be able to find another matrix which is noted by A inverse, which is basically when you invert its entries in a certain way. So why is this important? Because actually for 2x2 matrices at least, 2x2 matrices we know that if we have A, B, C, D, and you invert it, that's going to become D, negative B, negative C, and A. And then we're actually multiplying that by 1 on its determinant, which is AD minus BC, right? So to go from a 2x2 matrix to its inverse, we would be multiplying by 1 on its determinant in the front of that new matrix, in which case, if this becomes 0, then this is kind of like meaningless, right? It's null. So we cannot have that. So this is why, if we want to have an invertible matrix, we always have to have its determinant not equal to 0. Yeah. And then finally, if we multiply a row or a column of a matrix by a scalar, then the value of the determinant is also multiplied by the same scalar. So that's pretty intuitive. Yeah. So essentially, you can just like take the scalar out of the matrix or the row. Okay. So let's actually look at a question to see how we can apply this in our final exams. So here we have a 5x5 matrix A. And you can see it's actually, this is called a upper triangular matrix. So what that means is basically if you look at every leading term in every row, you always have zeros below it everywhere. So you look at -1, 1 plus k, 3 and -1, you always have zeros below it, besides -1, which is the last entry. So that's what determines what a triangular matrix is. Okay, so that's an important property about A. First of all, we want to calculate a determinant of a matrix defined by a squared minus 4a. Now, obviously, we're not actually going to calculate a squared minus 4a because this is like a huge matrix that would take you forever. So what we can actually do is here use the properties of matrices and matrix products, right? So we know that determinant of B should just be equal to determinant of a squared minus 4a, right? So looking at those properties that we revised a little bit beforehand, what we can actually do here is we can factorize the matrix a squared minus 4a. So we can factor out an a, and then we will get a minus 4i. So just remember, why do we get an I? Because essentially when you have a matrix multiplied by the identity matrix, you're just going to get the matrix itself. So then this would be equal to the determinant of matrix A multiplied by the determinant of A minus 4i, using this first property that we had up there. So it's really easy to calculate what A minus 4i is, because essentially for our identity matrix in 5, we just have, that would be 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 0, 1. So essentially, identity matrix is just when you have a 1 across the main diagonal, but everywhere else is 0. So for identity matrices, if you multiply by any matrix, you're just going to get like the matrix itself. Okay, so let's actually compute what A minus 4i is. When we're doing the subtraction of two matrices, we're really just looking at each entry and then doing subtraction on that position. So then A minus 4i would get us a new matrix, which is -1, -4, -5 on this. Everywhere else should stay the same because it's 0. 0, 0, and then 0. 1 minus 4, which is -3. -7, 0, 0, 0, 0. 1 plus k minus 4, which is k minus 3, 3, 4. And 0, 0, 0, 3 minus 4, which is -1, -7, 0, 0, 0, 0, -5. Yeah, so that is our new matrix A minus 4i, which looks a bit complicated, but essentially this is also beneficial for us because you know that if A is an upper triangular matrix, then A minus 4i must also be 5 because we're essentially only changing the diagonal parts of our matrix. So in this case, we can just find determinant of A by multiplying all of those entries on our diagonal. So we can do that for our upper triangular matrix, mainly because if you try like doing determinants properly, which is basically about reducing it to a kind of lower power matrix and continuously doing that, you realize that those zeros are just gonna essentially cancel off with a lot of your terms, such that you'll only get a product of the entries along the main diagonal. So then we can essentially just do -1 multiplied by 1 multiplied by 1 plus k times 3 times -1. That's our determinant of A up there. And then we can multiply this by determinant of A minus 4i, which is going to be essentially the same thing, but the numbers are slightly different. So -5 multiplied by -3 multiplied by k minus 3 and -1, -5. So this is pretty beneficial for us because we can factorize this and then compute it easily. So here we have 1, 2, 3, 4, 5, 6 negatives, which cancels out. So then we really just have 3 times 5 times 3 times 5, which is 9 times 25, which is 225, times 1 plus k times k minus 3, which our final answer would just be 225 times k plus 1 times k minus 3. So that is our final notation for determinant of B. That really helps with doing question 2, because 2 is just hence find all values of k such that B is not invertible. So recall if B is not invertible, well, if it's invertible, then its determinant cannot be 0, right? So if it's not invertible, this means its determinant is 0. So if we let determinant be 0, then we're just really finding the zeros to 225 times k plus 1 times k minus 3 equals 0. In which case, we'll get two values of k, which is either k equals -1 or k equals 3. And that concludes this example. So you guys can just take a look at the solution. Yeah, pretty much the same thing if I didn't make any algebraic mistakes. Right, so 225 k plus 1 k minus 3, and therefore the two values would just be -1 and 3. Yeah, okay. Okay, moving on from determinants. Actually, we haven't moved on. But anyways, moving on to more about inverses. So the inverse of a 2x2 matrix is pretty easy to find. As we said before, if we have a matrix which is A, B, C, D, then the inverse of that would just be equal to 1 in the determinant, which is AD minus BC. And then what you essentially do is you're swapping the positions of A and D. So then you get D and A. And then you're adding a negative to the B and C. And then that's your final inverted matrix. So with this complex matrix, we're essentially doing the same thing. So if we want to find the inverse of this matrix A, we're really just doing 1 on its determinant. Determinant should be 2 times alpha minus I times 1 plus I. And then we're inverting the positions of 2 and alpha. So we get alpha and 2. And we're just adding a negative in front of the positions of B and C. So we just get -I and -1 minus I. And that would be our final inverse of A, which is pretty simple. So it's like a one-step thing. And secondly is we want to find all values of alpha in the complex system such that the determinant of alpha squared, matrix A squared is equal to -1. So in this case, we can actually start from the given. So if we're given determinant of A squared is equal to -1, then what does that really mean, right? Remember that we can actually just take the power of this outside the bracket. So this is also equal to determinant of A whole thing squared is equal to, -1, right? So then essentially there's only two values for the determinant, which is either it's equal to one root of -1, which is I, or the other root, which is -I. And those roots are complex conjugates of each other. So there's really only two possibilities. And we can find determinant of A in terms of alpha from our original expression, right? So recall that determinant is really just 2 alpha minus I times 1 plus I. So that could be equal to I, or that could be equal to -I. And then quickly simplifying the expression, we have 2 alpha minus I plus 1 is equal to 1, or 2 alpha minus I plus 1 is equal to, that's I. So I or -I, right? And then to find alpha here, we just get that alpha should be equal to I on 2. And in this case, we get alpha is equal to, that's 2I minus 1 on 2. And this would be -1 on 2. So when you write the i's, just be careful of where the dot goes. Otherwise, it's very easy to make a mistake. But yes, that is our final two values of alpha for this question. So yeah, that is how you could write it as well. Yeah, so why can't we take the power outside is because essentially we're using that first property of determinants, which is that you can just, determinant of the product of two matrices is just the products of their determinants. And then finally get the two values of alpha. Okay, and then moving on to a very interesting question, which is more on simplifying matrices using different properties of transposes. Okay, so essentially we want to simplify this entire expression, right? So what's troubling us right now is that we have brackets everywhere, which means we can't really do anything about those individual terms, right? So we want to essentially take away the brackets first, such that we have just one sequence of only matrices and their transposes or inverses. So recall that with matrix inverse operations, the inverse of a product of two matrices is equal to kind of the reverse of the reverse of the products of their inverses. So what that means is basically you're just taking that -1, and then you're applying that to this one first, and then multiplying it to that one when you apply to it. So basically you just write it like this is equal to A inverse multiplied by A transpose inverse. So essentially you're swapping the positions when you take away the brackets. That's actually the same thing with transposes. So that is multiplied by A transpose of A multiplied by transpose of transpose of A. So you get this pretty long expression. But this is actually good for us because then we can simplify it. So nothing we could really do about this part. We can just keep that. But for the second part, we actually know that if we combine the transpose of A inverse with the transpose of A, this is like the inverse of a matrix multiplied by itself, right? So here we just really get the identity matrix because that's how inverses are defined. Inverse of a matrix is when you multiply that to the original matrix, you get the identity matrix. In which case, this is going to be A inverse multiplied by I. And then let's look at the final term, right? So finally we have the transpose of a transpose, right? In which case, if you just think about it, intuitively cancels out, right? Because you're first swapping the rows and columns, but then you're swapping them back. So that just gives us A again. And then this identity matrix doesn't really do anything because when we multiply it to anything, you just get that thing itself again. So that's equal to A inverse multiplied by A, in which case we would just get the identity matrix again. So that's our final answer. Just don't get kind of intimidated by those really long expressions. It's pretty simple when you start expanding it and kind of like recombining terms. But just an important thing to remember is that even though we're grouping terms in this case, we can't actually be moving things around because that would change the nature of our matrix products. So we just can't be like changing the order of anything in the expression. Okay, right. So that is the solution. Any questions? No? Okay, great. Oh, I'm registered. Okay, so finally, actually, I think this might be the second last question. We have kind of a three-component question, which is first one, suppose that we have matrices A and B for some values of A, B, C, D, F, G. We want to first find the determinant of A and determinant of B, which is really easy if you just remember the definition of determinants. So here, the determinant of A should be equal to AD minus BC. Determinant of B should be equal to AG minus BF. So if you add them, that's just going to be, that's going to be AD minus BC plus AG minus BF, in which we can actually do a little bit of factorization because that's beneficial for our next question. But that's A of D plus G minus B of C plus F. Yeah, that's our final expression that you could write. You could also write this one for the first one, but that would just not be as useful for our second question. The second part is you want to then find n, values of n, such that the determinant of A plus determinant of B is equal to n times the determinant of the sum of A and B. So how do we do that? First of all, let's find what A plus B is. So we can actually add A plus B because they're both 2 by 2 matrices. So then we have A plus A, B plus B, C plus F, D plus G, which gives us 2A, 2B, C plus F, D plus G. So then we want to find the determinant expression for this one, which is also really easy. So we're just multiplying the diagonals, subtracting them from each other. So that's 2A times D plus G minus 2B times C plus F. So if you actually carefully observe this, this is very much similar to our original expression for part 1, except we have an extra 2, right? So what we can do is we can factorize the 2, and then we have A of D plus G minus B of C plus F. So in this part, that is essentially just the sum of our determinants of A and B. Okay, so we have this expression right here. So what the question was asking us is, do you want to find the value of n such that n times this is equal to the right-hand side, right? So if we just look at that, right, we can really easily find that if you want this to be equal to just determinant of A plus determinant of B, then you really just want this part to become 1, right? So you don't want it to contribute anything. So that means 2n must be equal to 1 for this equality to hold true, which means n must take the value of a half. And that's this question. Let's just quickly scroll down to see the answer. Oh, okay, never mind. So you can trust me on this. I already did this question beforehand. So that is indeed the answer. And then let's look at question 3. which is you want to find the volume of a parallelepiped defined by the vectors, let's call them vectors A, B, and C. So what a parallelepiped is essentially it's like a parallelogram, except you have like a 3D shape of it. So it's like let's just draw that quickly. So it's kind of like this. Not very good at drawing, but yes, let's just say this is vector A, this is vector B, and this is vector C, right? So essentially, if you have any three vectors, you position them correctly, like by shifting on the plane, you'll be able to get a parallelepiped defined by those three vectors, as long as they're not parallel, right? In which case, you could quickly check none of them are parallel. So then we can indeed find a volume for this parallelepiped. So how do we actually find the volume? Is if you look at those three vectors, right? So the volume of any 3D object is we can use the formula base times height, right? So in which case we can really choose anything for the base, but just for convenience, let's choose this base, which contains vectors A and B. So how can we find the base, the area of the base? This is essentially finding the area of a parallelogram defined by A and B. Right, in which you guys should have learned that is just going to be the cross product of vectors A and B and taking the magnitude of that, right? That would be the area of the parallelogram. Okay, and then what do we want to do with that area? We want to multiply it by the height going in this direction, right? So recall going in this direction, we want to find that height in terms of C. So how do you find that height in terms of C? Well, if you do some 3D trigonometry, we can kind of like draw a triangle here. So this is going to be vector C. This is going to be a vector that was perpendicular to both A and B, which is basically just their cross products. And then there's going to be an angle there, right? So this angle, how can we kind of find this angle? This angle is really just the angle between the normal vector to both A and B and our new vector C, right? So then how can we kind of write this formula? We want to find this height, right? Using the definition of cross products, our final volume would actually just be A cross B dot C. Because dot products, recall, contains the cos of that angle already, in which if you multiply cos of that angle to this vector, to the magnitude of this vector, you're just going to get that vector, right? Because this is a right angle triangle, essentially. So then we can simplify the final volume using this formula. And this formula works really like any way. So you can define A, B, C as any random three vectors. So in this case, let's just plug in the values of vectors A, B, and C. So we're really finding 1, 0, 0, 0, negative 4, 0. So 1, 0, 0, cross 0, negative 4, 0, and then dot negative 1, 1, 2. Right. So then you're finding the magnitude of that final value of whatever you get. So essentially, if you compute it, this is pretty easy. This is just going to be 0, and then what's the second row? Right, 3, 1, that's still 0, and then negative 4 dot negative 1, 1, 2, which is going to get us negative 1 plus. Oh, sorry, that's 0 plus 0 minus 8. And then take the magnitude of that, right? So if you take the magnitude of that, that's just going to be 8 at the end. So that the volume of this parallelepiped in 3D space is going to be 8 cubic units. And then that's how we could approach those questions. So just remember to check if those three vectors are actually like all non-parallel to each other, because if they are parallel, then you're not going to get a 3D shape. In which case, like most of the question, they won't find vectors like that. But yeah, you can just check that yourself. Okay, and then moving on to kind of an extra question, which is still on determinants. So determinant is a very interesting concept in matrices. You guys can kind of like revise a little bit about like different properties of determinants with matrix products and such. That would be useful. Okay, but this question is basically telling us that we have a matrix of A, B, C, D, which has a determinant 4. So let's write that. That basically just means AD minus BC is equal to 4. That's what they told us. And using that, we want to find the determinant of the matrix 2A, 200B, C, 100D. If we look at the new matrix, right, it's actually very easy to see that A, B, C, D, like the relative positions of them hasn't really changed at all. We really just changed the coefficients. So this is very useful for us, because if we just change the coefficients, our new determinant is going to be is going to be 2a times 100d minus 200b times c, which actually both have a coefficient of 200. So let's just factor that out. Then we have AD minus BC, which we know is equal to 4 from our original matrix determinant. So this is just going to be 200 times 4, which gives us 800 in the end. And that is our final matrix determinant. Any questions? No? Great. Okay. You guys are very sure with matrices. Okay. Moving on to complex numbers, which many of you probably did in high school. So it's more like a recap of complex numbers. So first of all, we have the Moss theorem, which is basically just when you have a complex number, you raise that to the power of n, then you can take the n in and apply that to the angle. So yeah, essentially just like thinking about rotating that matrix, rotating that complex number continuously in the complex plane. Okay, so let's just look at the question, because usually those come in the form of finding, let's say, like finding what cos n theta is as a polynomial of cos theta, or it could be sine n theta in terms of sine theta. So essentially, we're always using the Moss theorem for those questions. How do we do that? Part 1 is we know that using the Moss theorem, we know that cos 4 theta plus I sine 4 theta, that should be equal to cos theta plus I sine theta to the power of 4, right? Because we can just take that power inside. So then we can expand the right-hand side using binomial theorem. So that's cos power of 4 plus 4 choose 1 cos theta power of 3 I sine theta, and then so on. So I'm not going to write all those terms out, but basically there's going to be 5 terms in this expansion. Okay, so how do we find an expression for cos theta? Observe that for some terms in this expansion, you're going to get an I there, right? Which is going to match with the imaginary part of that final number. Because we want to find cos theta, which is really only the real part. So let's just compare real parts of left-hand side and right-hand side to get an expression of cos theta. So on the left-hand side, we just have cos 4 theta. Right-hand side, if we're getting rid of all the i's, we're really just taking the first, third, and final term, which is going to be 4 choose 0 cos the power of 4 theta minus 4 choose 2 cos square theta sine square theta. So the minus comes from I squared. And then finally, 4 choose 4 sine to the power of 4 theta, which is just cos 4 theta minus 6 cos square theta sine square theta plus sine to the power of 4 theta. But now the question wants us to express it in terms of cos theta only. So essentially, we just convert everything to, we just convert all the sine squares to 1 minus cos squares. So this is 6 cos square theta times 1 minus cos square theta plus 1 minus cos square theta to the power of 2. So let's just count all the terms in cos power of 4. So we have 1 here, we have 6 here, we're going to get another 1 here, so that's 8 cos power of 4 theta. And in terms of cos square theta, we're going to have minus 6 here, and then another minus 2 here, so that's minus 8 cos square theta. And then finally, we're just going to get one constant term from the last expansion, which is 1. So by comparing real parts of left-hand side, right-hand side, we can determine that and polynomial expression of cos 4 theta is as such. Okay. So part 2 is hence or otherwise, you want to find the roots of a polynomial defined by px is equal to 128 x to the power of 4 minus 32x squared plus 1. So essentially, we're obviously going to be using part 1 to do this question, right? If we look at the coefficients carefully, you realize that if in part 2, if we just let x be equal to a half cos theta, and then we put that back into our, this expression, if we put that back into the polynomial expression, which was px is equal to 128 x to the power of 4, minus 32x squared plus 1. If you plug that into this, that's going to be equal to 128 times 116 cos to the power of 4 theta minus 32 times 104 cos squared theta plus 1, right? So if we simplify that a little bit further, this is actually equal to 8. So that's 8 cos 4 theta. That's also equal to 8 cos squared theta plus 1. which is actually just our expression for cos 4 theta. So we can simplify px then into cos 4 theta. So we know that if we want to find the roots of px equals 0, we're just really finding x is equal to a half cos theta, where theta is a root to cos 4 theta equals 1, right? So to find the roots to cos 4 theta equal 1, that's just, so 0 is, sorry, 0. So 0 is essentially cos pi on 2, 3 pi on 2, 5 pi on 2, and so on. But how many solutions should we be finding for this question? Well, you know that the highest degree of this polynomial is 4, right? So you really need to just find 4 different solutions, in which if you plug in just those angles, they will give you 4 different solutions. So then we know that x equals a half cos, remember to divide this by 4, by the way. So that's a half cos pi on 8, a half cos 3 pi on 8, a half cos 5 pi on 8, and finally 7 pi on 8. That would be our 4 solutions to this polynomial. And the final part of the question is, by examining the roots of px, we want to find the exact value of sine pi on 8 multiplied by sine 3 pi on 8. So first of all, if we look at just this expression and those roots that we have, sine doesn't really appear anywhere, right? But it told us to examine the roots, and we have kind of like a product here. So we want to consider, first of all, consider the products of roots in this polynomial. So just look at this polynomial. We will know that products of roots, let's say x1, x2, x3, x4, that corresponds to the 4 different half cos respectively, is going to be equal to, this is a, b is going to be 0, c is 0, c is negative 32, d is 0, and e is 1. So the product of that is going to be e on a, which is going to be 1 on 128. Right. So essentially we know that cos pi on 8, cos 3 pi on 8, multiply everything until cos 7 pi on 8 should give us 1 on 128 after factorizing out the coefficients. So what that basically means is if we multiply all of them, in which we're going to get a 1 on 16 coefficient, right? That should get us 1 on 28 as a product of roots. So then we would just know that if we only multiply these only, that would be equal to 1 on 128, what was the factor? And 16, right? So that would be equal to 1 on 8, yeah? So why is this useful? Because due to complementary relationships between cosine and sine, we know that sine of an angle, well, actually let's start with cosine. So cosine of an angle, let's say pi on 8, that's going to be equal to sine of 9 degrees minus that angle, right? Because they correspond to the same sine ratios in a right triangle if you draw it out. So then that's just equal to sine 4 pi on 8 minus pi on 8, which is sine 3 pi on 8. Similarly, we can express all the other different cosines in sines. So cos 3 pi on 8 should be equal to sine pi on 2 minus that, which is sine pi on 8. Cos 5 pi on 8 is equal to the negative of cos 3 pi on 8, which is just equal to negative sine pi on 8. And finally, cos 7 pi on 8 is equal to negative cos pi on 8, which is just equal to negative sine 3 pi on 8. So as you can see, we've expressed all of our original roots now in terms of sine, in which if you multiply all of them, you're going to get sine pi on 8, sine 3 pi on 8 squared is equal to 1 on 8. So then that means there's really only 2 possibilities for our product that we want to evaluate. And it's going to be either 1 on 2 root 2 or 1 on negative 2 root 2, right? In this case, because sine pi on 8, sine 3 pi on 8, both of those angles are acute. So we know that the sine of those angles should also be positive. So this is going to be the answer that we take for the question. Yeah, and here is a typed up solution, which you can take a look at if you find my handwriting hard to read. Yeah, okay. Yes, as you can see in the end, we get that expression. And then finally, we get that that's equal to 1 on 2 root 2. So it is important to write this line because then you're justifying why you're only taking the positive case. And then moving on to roots of unity. So essentially what roots of unity is when the question tells you, let's say, z is a third root of unity. What that means is just that z to the power of 3 is equal to 1. That's really what it means. And what's special about this root is that the modulus is always equal to 1. Which is very evident if you just take in the power and use the Moss theorem. Okay, so by considering seventh roots of unity, you want to find a set of non-real solutions. So this is also important. So then you don't want to include any real solutions. To the equation, 1 plus, I want to say that's omega, to the power of 7 is equal to 1 minus omega to the power of 7. Okay, so this is actually in a very unfavorable form because we don't usually typically solve polynomials like this. We want to get this into the form of, let's say, z to the power of 7 is equal to 1, right? Because then we can actually consider the 7 roots of unity and then be able to find what z is, and then hence deduce what omega is. So what we can do first is we can divide everything by 1 minus omega to the power of 7, and we know that omega cannot be equal to 1 for this reason. But because we're finding the non-real values anyway, so it's not going to be equal to 1, so that's not a problem. So then we would get 1 plus omega to the power of 7 divided by this is equal to 1, or we can write it as one whole fraction. Sorry, this is equal to 1, right? So in this case, we can actually let 1 plus omega over 1 minus omega be equal to some complex number z, right? And we know that for this complex number z to the power of 7, that's equal to 1, which means z is a seventh root of unity. So how to find the seven roots of unity, like for the 7th power, is essentially we can let z be equal to e to the power of I theta, which means e to the power of I 7 theta is equal to 1, which is also equal to e to the I 2k pi, where k is any integer. So we usually just add in a random, introduce a random variable, so such that we can take different values of that variable and then find corresponding values of theta. So in this case, we would know that 7 theta is equal to 2k pi, or theta is equal to 2k pi on 7. And then we can take different values of k. So k equals 0, you're going to get theta is equal to 0. K equals 1, you're going to get 2 pi on 7, and then so on. And then we can actually end at k equals 6, because you'll notice that if k equals 7, you're just going to get 2 pi, which is actually the same case as 0, because that's one full rotation. So we end at k equals 6, which gives us 7 roots, and that is going to be 12 pi on 7. It's also okay if you write this as, let's say, negative 2 pi on 7. Doesn't really matter. It's essentially the same thing when you do EI. Okay, so then we have 7 roots, and how can we find our original root omega? Then we need to find omega in terms of z, which we can do that by just rearranging this equality. So that means 1 plus omega is equal to z minus z omega by moving the bottom to the right-hand side. And then combining all the in omega, we would have z minus 1, in which case this is going to be equal to z minus 1 on z plus 1. Right. Okay. And then basically, why is that useful? Because we know that what z is from this, right? We just need to exclude one of those roots, which gives us a real root, which is when theta is equal to 0, because then z is just equal to 1, which we don't want, because the question was asking us for the non-real roots. So we're really just taking k equals 1 to k equals 6, and then finally we'd be able to simplify that expression. So omega is z minus 1 on z plus 1. So there's multiple ways of simplifying this. You can write that as ei theta minus 1 on ei theta plus 1. And then that's also equal to, you can multiply by negative ei theta on top and bottom. That gives us 1 minus e. Oh, actually, that's not very useful. But actually, if you'd like to tend to switch it into polar form, then you can write this is equal to cos theta plus I sine theta minus 1 on cos theta plus I sine theta plus 1, in which case you can use double angle identities, and then at the end you would pretty much be able to get this is equal to I tan of theta on 2, right? And then the theta values are really just the values that you found from there. But then in the solution, they simplified it a slight different way, which is they just multiply top and bottom by e negative I theta plus 1, such that you get an expression like this, which if you use double angle, you're going to get the same thing. But it's okay if you just also put it in that form. Basically, you just want to rationalize the bottom part of the fraction, and then just plug in values of theta that you found as a solution to this, and you'll be able to get all of the roots. So, yeah. So they listed that as a set, which you can also do in an exam to avoid biting too much. Okay, that really concludes my section for matrices and complex numbers. Do you guys have any questions? No? Okay, in which case, welcome to come to our Friday's revision seminar, which goes through, I believe, calculus section, which is like intermediate value theorem and so on. That would be pretty useful to help you guys revise for your exam. But otherwise, good luck with all your lab tests and exams, and that is the end of this revision seminar. Thanks for coming, guys.